eventually I will talk about Fedosov quantization, but I want to start, well, my kind of the general topic of my talk is deformation theory. So I start with a very general setup. So I fix some field K. So it can be C, FP, or some other field. And I fix an algebra, A0 over K. And then I'm interested in deformation of these algebras. So what I mean by this is that for uh, for any local Artinian algebra, K algebra, or so with a such that the residue field is K, I'm interested in deformations of A0 over R. So this is by definition a flat R algebra. Okay, with an isomorphism. This. Okay. So, and the question is, well, the question is how many deformations we have. We want kind of, can we sort of classify all of them up to isomorphism? Well, I don't think that I can anything meaningful to say in this general setup. So, well, maybe before I continue, so I don't assume that my A is commutative. However, I'm going to assume that A0 is commutative. Moreover, I will assume that it's smooth. So assume from now on that A0 is smooth commutative over K. So, well, then at least, well, under this assumption, at least we know that there are no commutative deformations. So any such A is isomorphic to just tensor product of A0 and R, any commutative. But there are non-commutative deformations. And, well, maybe to so here is a maybe first example. So let's classify all square zero deformations. So let's assume that m squared is equal to 0. So in this case, I claim that deformations. So you can think of, for example, a good example to consider is when R is a ring of dual numbers. So in this case, deformations over R, isomorphism classes of deformations are in one-to-one correspondence with bivector fields. So I consider the tangent sheaf I consider it wedge 2, and I tensor it over T with the maximal height. So Well, you can think of this as this is the same. Well, this set is this is set of bi-derivations. So maps from A0, tensor A0 to well, even let's say wedge 2 of A0 to A0 tensor M. So kind of brackets with the property that they are derivation with respect to each variable. So meaning that A comma B C is equal to A B times C plus A C times B. Right? So, well, so let's at least construct a map in this direction. So the construction is very simple. So if I have E over R, so I want to define for you this bi-vector field, this map, and so by definition, a sort of this bracket is equal to, well, you take, so we have a map from A to A0 given by this isomorphism, and we can take an element A and leave it arbitrary. And the same is B. So, since my algebra is commutative, this commutator lives in A tensor maximal ideal, and because M squared is 0, it actually lives here. So this defines the bi-vector field, and a theorem, particular case of Hochschild-Kosten-Rosenberg theorem, is that this map is always nice. All right. Are there any questions so far? All right. So now, so this is first order deformations. So what about second order deformations? So example, suppose my R is well, suppose I have a well, let's consider deformation over K of H modulo H. Well, so if I have a deformation over such R, in particular, it gives me a deformation of the do numbers. So, and deformation over the do numbers are classified by this bi-vector fields. But the problem is that not every deformation A1 over K of H modulo H squared extends to a deformation over R. So, in fact, there is a condition on this bi-vector field that guarantees that such deformation extends. So, what is this condition? Well, so So the commutator has an additional property. The commutator in any associative algebra satisfies Jacobi identity. So we have so A1, and this gives me a map from this bi-vector field, which is well, this is this lives here, but I can consider, well, since I have a generator in the maximal ideal, I can sort of divide this by h, right? So any first order deformation gives me such a map. And I claim that if deformation extends, then this map should satisfy the Jacobi identity. Well, I think it's usually, well, one just identifies M with K and erases H. That's what I'm going to do. So then I claim that if A1, A1 extends to a deformation, if and only if this bi-vector field satisfies Jacobi. Right. So why is that? Well, so again, so this always satisfies the Jacobi. But if I write it in this way, then the Jacobi identity is kind of it's empty because h squared is equal to 0 in that. But it's not empty when I can work modulo h cubed. And this gives me the Jacobi identity for this. All right. So at least in one direction, it is clear that this is a necessary condition. But the claim is that the inverse application also. All right. So, and if this condition is satisfied, then you can then by this statement there exists at least one extension of this deformation over R, and you can see that the set of such extensions is a torsor again under bi-vector fields. So that's the that was all known at least to Hochschild a long time ago. But if you want to like describe the isomorphism classes of all deformations, say over formal power series of H, this method does not kind of, well, you have many abstractions, and then for each abstraction you can do something step by step, but then controlling abstractions becomes complicated. So now so at least in the case when K has characteristic 0, the problem of describing commutative associative deformations of a smooth commutative algebra is completely solved by Kontsevich. So this is a deep theorem. So this is 1997. So his theorem says the following, that deformations over R, the isomorphism classes, are in one-to-one correspondence with bi-vector fields. So now you take A0 and you take Vach2 of TA0 considered with maximal ideal. So again, I think of this as a map of A0 Vach2 to 0 M that is by derivation and satisfies Jacobi identity. So I hope at least it's clear that it's consistent with the first example of square zero deformation that I gave. So in that case, Jacobi identity is actually empty. All right. So well, the way I formulated this theorem, well, it's kind of you may think that it's sort of empty. I didn't tell you what the bijection is. Well, you're just saying that two infinite sets are in bijection. That's not very useful. But well, this bijection satisfies various compatibilities, in particular with base change on R. So if you have a map from R to R prime, then base change deformations and also bivector fields. And this already implies something non-trivial. For instance, corollary of this is that for every Poisson structure on A0, let's maybe give it a name. So again, the Poisson structure is a by derivation. It's a map like this that satisfies Jacobi identity, the usual Jacobi identity. There exists deformation of A0 over formal Fourier series such that for any two elements, the Poisson bracket is equal to, well, is equal to the commutator. You take any two lifts, divide the result by h, and take the result mod h. All right. So that's already something highly non-trivial. So, well, so I'm not saying that, and this is not true, of course, that such a deformation is unique, but there exists kind of a distinguished deformation. So this well, Kontsevich bijection is given by some explicit but complicated formula. So he just writes down, so given a bar vector field satisfying Jacobi identity, he constructs the start product. He constructs the deformation by some explicit formula involving some integrals over integration space. So but however, this deformation is not canonical. So remark. So there exists a deformation, A, H. So A sub h is not canonical in the following sense. So if I consider the automorphism group of A0 that preserves this Poisson structure, well, it acts topologically on A0, but in general, this section does not lift to A0. Well, in fact, this can be already seen in the commutative case. I mentioned that if A0 is smooth, then every commutative deformation is trivial, but it's not kind of canonically trivial. And globally, if you consider you replace affine varieties by something non-affine, there are non-trivial deformations. Something similar happens here. So it's not quite canonical. However, what is true is that, however, this group of symplectomorph, of Poisson automorphisms of A0 acts on the category of mode on A. So another way of saying it is that even though AH is not quite canonical, the category of modules over this distinguished quantization is well defined. And in particular, it can be globalized. So I describe for you the notion of quantization or deformation of a affine Poisson variety, but in general, well, you can consider non-affine, and so if you can kind of quantize affine varieties in a canonical way, then you expect that this construction glues, and that's the case.
Yes, for the commutative case.
For the commutative case, right. So what is the that's a good question. So so what happens if you consider the well, I mean, I don't know. So I said that there exists a distinguished quantization. If the Poisson bracket is 0, then this my distinguished quantization is just trivial.
Yeah, this argument's off.
Yeah, I agree. So, but nevertheless, this distinguished quantization is so functorial that you conclude. All right. So this is, I think, this remark is, well, it's somehow it's implicit in Kancevich's original paper, and was developed in details by Yekutili and in more details by Van der Berg. So this is the field.
So the assumptions on this view,
no assumptions, smooth. Yes. So all right. So now so in this talk I will consider much simpler situation when my Poisson structure is non-degenerate. So So what is a Poisson structure? So it's a biovector field. So it's a so let's say we have let's introduce geometric notations. So then, well, a biovector field is an element, is a fraction of the sheaf. So it's a skew-symmetric form on the tangent space. So it's a map from dx dou to itself. And we say that it's non-degenerate if this map is an isomatrix. So in this case, I can consider the inverse map. And this gives me, well, it gives me a map from Tx to the dou space. So it gives me one form. Two form, yes. Omega 2. And the fact, the Jacobi identity for the Poisson bracket is equivalent to saying that d of omega is. So non-degenerate Poisson structures and one-to-one correspondence with symplectic structures. I'm also only going to consider this talk quantizations, deformations of symplectic varieties over various fields. This is much easier theory, and the main result is this symplectic version of the Kontsevich theorem for symplectic varieties. Well, it's essentially proven by Fedosov, and so that's why it's called Fedosov quantization. And well, he worked with smooth manifolds, and I think in algebraic setting, it's written down by Bezrukovnikov and Kaledin. But already in this case, there is no canonical quantization of the algebra, but the quantization of the category is canonical. So I want to formulate this. What do I mean by quantization of a category? So suppose I have a 0 and I have Poisson bracket. So a categorical quantization well, it's a category over K double bracket H, which is flat. So it's an abelian category, which is flat. So what does it mean? Well, there is a notion. So if you have a category which is co-complete over a ring, then you can tensor any object of this category with a module over this ring. In particular, you can talk about flat objects of the category. These are objects that the tensor product functor is exact. And flatness of a category means that every object, there are sufficiently many flat objects that any object can be covered by a flat. There is slightly more general notion, which is studied by van der Berg, or maybe not. I don't need it. So, so categorical quantization. Well, it's this flatness condition plus c times k of h. In equivalence, it's the deformation of the category of modules plus certain compatibility condition with this Poisson break. So perhaps the most conceptual way would be to use to formulate it using Hochschild homology, but I can do without. Let's just observe that. So if I so there is a following condition. So it's again, this condition is analogous to, it's a categorical analog of the fact that the commutator mod h squared is this Poisson bracket multiplied by h. So how to formulate it? Well, in fact, for I can consider a module, regular p module over A0 for any lift flat of A0 to C. And the fact is that in this setting, such flat lifts always exist. You can study abstraction. So in this very general setting, when you have a flat category over K double bracket H, you can study abstraction theory. You can start with an object of this tensor product and ask whether there exists a flat lift of this object. And the abstraction lives in X1 from this object you started with to itself. So my object A0, this is a projective module. So X1 vanishes. So you can always find a flat lift. If I fix such a flat lift, then I consider endomorphism multiple of M. And I can consider the dual algebra, opposite algebra. And the requirement is that is deformation of okay. So this is this construction explains the difference between categorical quantization and deformation quantization of algebra. So deformation quantization of an algebra is the same as a categorical quantization plus a lift. And you see that this lift, although it exists, well, by the way, I said that the abstraction is in X1. It's actually in X2. But the set of lifts is the torsor of X1. So such a lift exists, and all such lifts are non-canonically isomorphic. But because of this non-canonicity, there is a difference between categorical quantizations and quantization of algebra.
I don't understand this lift M. Is it trying to extend A0 as a biologic?
No, I mean, imagine that C is actually modules over A sub H.
Left modules.
Left modules. Then I can choose for such a lift A sub H. All right? And then what is endomorphism? in my category. So what happens if you consider endomorphisms of A sub H in the category of A sub H modules?
Function H.
Well,
So
it should be A sub H obviously.
yes.
So saying that this sort of construction applied to the category of A sub H modules recovers for me A sub H. Right? So that's the intuition here.
So in particular, this place of lift, they don't see the quantum circles.
Sure. Yes. Yes. Very good remark. So yeah. So this is A sub H. Then in fact, modules over A sub H included. All right. Very good. So now I will formulate a result of Bezrukovnikov and Kolezin. This is a special case of more general theorem of equity and Vanderberg, but it's much easier to prove. Maybe there will be a complement to this to Ginsburg. Well, there are two statements. Well, I formulated geometrically. So for every symplectic you will not lose anything by assuming that x's are fine, as I did, but you don't have to do this. So over a field K of characteristic 0, there exists a canonical categorical quantization. Quantizations. So that's H. That's the first remark. That's the first part of the theorem. And the second part, well, so what makes it actually useful is that you can produce objects in this canonical quantization. So this is a category over formal power series in H, and if you mod it out by H, you get this category. So you want to quantize, you want to lift some objects here to objects here. What kind of objects we want to lift? Well, what are your favorite quasi-coherent sheaves on X? Well, for instance, we can consider the structure sheaf of some varieties of X. There is a very general result of Bernstein and Gaber that says that if your subvariety, let's say, in X is too small, meaning that it has dimension less than half of the dimension of X, then this structure sheaf of L cannot be lifted. It cannot be quantized. And if the dimension is small as possible, so it's half, then L must be Lagrangian. Well, they work with not necessarily smooth submanifold subvarieties. But let's assume that. So for any, let's assume that L is smooth, then the result in particular implies that it's Lagrangian. So for any Lagrangian, and any choice of square root of the canonical sheaf on L. So this K is omega dim L. So this is a line bundle, and this is another line bundle whose Standard square is K. There exists a canonical object, which is let's say O L H in this categorical quantization that leads well, so sorry, of course it leads this. That's why I need it. Yes, thank you. So an example, for example, if I have a map, a symplectomorphism of X, a map from X to X that preserves omega, then we can consider its graph, and this is a subvariety of X squared. And if I endow X squared with a symplectic form, omega plus, well, omega comma minus omega, then this is Lagrangian. So I can by this part B, I can quantize those Lagrangians, and this gives me some bimodules over, well, endofunctors of this category. So that's in particular implies that every symplectomorphism of X leads to a symplectomorphism of this kind. Okay?
So there's no notation to general Poisson quantity.
I don't know. I don't know.
But because somehow one somehow but it's itself doesn't say that we talk.
Yes.
And there's no notation to singular.
Очень nice. That would be very good. That's what indeed what would be very useful. So all right. So now so I want to explain for you, recall for you an idea of the proof of this theorem. And what is nice about this theorem is that it doesn't have anything to do with X. So so proof, well, it will be a sketch of proof. So the proof consists of 4 steps. Well, the first input is Darboulin. So it says that every symplectic form on the formal disk. Y1 n has a form. Or is any, well, any KL has the form, well, omega is sum of standard form, dxi, wedge dy. So in other words, there is a automorphism of this formal disk that brings my omega to this.
What is it? What's in that term? Right,
Oh, it's relative. It's relative. This omega is is a section of its relative term. So I'm just saying that you can do it for field, but you can also do it in family, provided that the base is. Okay, so that's the first step.
How does that, you don't have to define the scenario?
No. Well, it's R is a K out. Not necessarily smooth anything. So the second step is okay. So the first step says that well, all symplectic varieties are locally look the same, but locally in this very strange sense, in the formal sense. So then the idea is to quantize things locally and then glue. Okay, so construct quantization of this guy R, well, K well, n with form omega equal to sum dxi dy. Okay, so well, and that's we can do it explicitly. In fact, in this case, we can construct an algebra quantization. So we define A sub h. Well, we consider the Weyl algebra. So this will be K x1 y. And that's just a kind of algebra. Okay, so there is also h here, which is a central element. And the relations are that commutator of yi x j is h times delta I. And all other variables commute, and h is in the same. So this is an algebra over polynomials in h, and I want to h complete. All right. So this is a kind of what's called the algebra of h differential operators on the affine space. That's on the affine space, and then you do something, you complete. You completed, sorry, with respect to h, yes. With respect to h and also xi, because I want to consider formal power series. So so this gives you, when h is 0, it recovers this algebra, and you can see just from this formula that this gives you the desired person. Okay, so this is the first two steps. And the last step, well, there was two. So we want to explain, we want to glue it. So, and to glue it, you the main input is the following. So let's let's consider the following group. Well, so I will tell you what our points of this group are. This is just the automorphisms of the formal disk over R that preserves some map. So what I defined for you is functors from rings to groups. But it's not representable. So G0 is not quite a group, but it's a group in scheme. It doesn't matter for me. So it's just I think of this as a functor with values in groups. What?
Is it an E?
No, it's a group in schemes.
Oh, that's what I'm.
Yeah. Yes.
Who else would get this?
Yes. So and then the main thing is to construct action of G0 for of symplectomorphisms on the category of modules over this A sub H tensor is now in complete sense. So so you want to kind of say that this construction is functorial with respect to all automorphisms.
Why you need to have this quantized Lagrange and if you compare Lagrange this will give you this.
It will give me this. Yeah, yes, it's more, but I mean, I'm not going to explain at least now how to quantize Lagrangians, but it's also used the same. Yeah. And 4, use what's called Gelfand Kazdan formal geometry. So glue. Well, to get football. Okay, so in fact, the main step is 3, but I want to give you some more details about 4. So imagine that you want to define the notion of differential form on an algebraic variety. Well, one way is to open EGA, and then you can find a fancy definition with a conormal sheaf and so on. So suppose you kind of mind that you want to coordinate definition. You want to define it in coordinates. So for smooth manifolds, what you need is you have to define this vector bundle differential forms over a disk, and then for any map between disks, you have to explain how you pull back differential forms. In particular, you have to explain how differential forms change under change of variability. So discovery of Gelfand and Kazdan is that, in fact, you can do the same in algebraic geometry, where actual disk is replaced by formal disk. And once you know what differential forms on an object like this on the formal disk are, and you know how automorphisms of this formal disk act on space of differential forms. So how this is differential forms is a representation of the group of automorphisms, you can define it for any x. And so the idea is to consider the following assigned to every x the torsor of coordinate frames. So, so what is this? This is a actually a scheme that whose S points consist of a map from S to X together with, so if I have a map from S to X, I get a, I can consider its graph. And what I want is an isomorphism between the completion of S times X along the graph and the formal disk. S times spot of my out K of X1 and so on. So in other words, an S point, or well, a point, or K-valued point of M is a point of X together with a coordinates, formal coordinate system, an isomorphism between the formal neighborhood and this disk. So there is one condition that I missed here. So this is which is it must be, it's very important, which is identity on S. So S sits here as a graph, right? And also, so here this S sits as a kind of the origin of this formal disk, right? So I consider only coordinate systems which, well, xi, which are actually equal to 0 at my point. So now, so this is a torsor under the group of all automorphisms of this formal disk that preserve the origin. And the observation of Galfand and Kazhdan is that there is a this total space has an action of a larger group of all automorphisms of the formal disk that need not preserve the origin, right? You can, if you, of course, if R is reduced, then every continuous automorphism of this ring must preserve the origin. But if R has nilpotent elements, then you can, for example, consider infinitesimal translations of the formal disk. So automorphism of R K. So this is considered as a group valued function in object. All right. So, and if you take the quotient, then of this space by the group of change of coordinates, you get the Durand stack of X. So in particular, if you have a representation, let's give me a name to this group. I will call G Galfand Kazhdan. Galfand Kazhdan. If I have a representation of this group, or I have a torsor under this group, right? And if I have a representation, I can consider twist of this representation by this torsor and get a well, quasi-coherent sheaves actually a vector bond. Over at Durand. So you can think of this as a vector bundle over X with a connection. That's the same thing. And then you take the global sections, flat sections. So I'm explaining how we gives me 4.
So what the set is that we have representation was
Yes.
it's like the bundle connection.
And then I can take its split.
And this is what?
And this will be my answer. So here I have a categorical representation of this group.
Okay.
And what I produce is a category over this space. And then I take its split.
But when we have the same, the doors are smaller.
Over the smaller group, right? So that's not so here I need a representation of the whole group, but imagine that I have a symplectic structure. Then I can consider a subtorsor of their book coordinates, and this is a torsor under this group that I call G0. So if I have more structure on my algebraic variety, then can I reduce the structure group of this torsor to a smaller group? And that's the main idea.
I'm confused, but I'm how this thing doesn't. So it's a torso over whether it's zero or I mean that is conditional whether origins preserved or preserved.
So you get an object here.
So when you pass don't have the same story.
Yeah. I mean, here I do not assume that the origin is preserved.
But then
well, this whole thing is a torsor. This is only a torsor under the subgroup that preserve the origin. So that's kind of the idea. It's not. I was sloppy here, and I just explain where I was sloppy. The representations I'm actually interested in are not kind of algebraic representations, whatever it means for such a group. They're rather projective limit of algebraic representations. And objects that I get here, this vector bundles with connection, are not really like quasi-coherent sheaves or quasi-coherent sheaf of categories over this stack. A good example to consider is a jet bundle. Jet bundle is not a quasi-coherent sheaf. So, but it's a pro object with a connector in the category of vector bundles. So there are some technicalities that has to be solved here, and this is this was kind of this picture was explained in details by Wanderberg. Unfortunately, only in perspective 0, but it's not really good. So, modulo this, the main ingredient is 3. And so let's just think what it means. So what is written here? So this is a category. So what does it mean for a group to act on a category? Well, so apparently, so we have G0, and we want to consider the group of autoequivalents of a category. So what kind of object is this? So we want to have such a map, but what is the right-hand side? So the right-hand side, this is some abelian category, and what is a group of autoequivalents? What kind of that's definitely not a group in the usual sense, right? Because you have autoequivalents, then you have natural transformations. So that's rather a group object in group weights. This is a 2 group. And so what we want to have here is a map from a usual group to a 2 group. Well, fortunately for 2 groups, there is a very simple kind of module, which was I think discovered by it's called cross module. So so if I have a actual automorphism of my algebra AH, then it definitely gives me an autoequivalence, right? Because all automorphisms act on the category of modules. But if my automorphism is inner, then I should declare this autoequivalence to be isomorphic to the trivial autoequivalence. But this isomorphism depends on the choice of an element of A cross that I conjugate. So there are this group is well, it's the structure of this two group is described by this map. So well, that's a map of non-commutative groups. It's phi 0. So automorphism of AH modular the inner automorphisms is well, one has to check it. It's my group G0, and but it also has pi 1, which is the center of this. That's called the positive loop group. So R-valued points are invertible elements in R double bracket H. So our plus GM of R is R of H invertible. All right. So that's the kernel. And what I want is a map from G0 to this two group. Well, that is identity on pi 0 that splits it. What I want to show is that this two group is in fact a product of G0 and something else. Semi-direct. So what does it mean concretely to construct such a split? Well, that's equivalent to saying that you have an extension of this group G0, how you split a length 2 complex. When a length 2 complex is what does it mean to say that a length 2 complex is isomorphic in the derived category to direct sum? Well, it means that you have an extension. Given such a splitting is equivalent to given an extension, a diagram like this. All right. So this is an extension of G0 by the quotient of H cross by the center, and you want to leave this to an extension of G0 by H crosses. So that's a key input of the construction. Once you have this, you are done. And so the construction of G02 is very simple. So you look at the Lie algebra. So this is the group of automorphism of AH, and this the Lie algebra. So you just consider the AH tensor dual numbers and consider automorphism, which is identity modular H. And the claim is that they're almost inner. Namely, this is the following. So you consider A sub H. This is an associative algebra. In particular, it's a Lie algebra with respect to commutator. But the claim is that because the commutator A0 is commutative, this is also a Lie algebra with respect to commutator. When you commute two elements which have only first power of H in denominator, it still has the commutator has only first power of H in denominator. Right? And that's so any element here acts here by commutator. And this is almost an isomorphism. Namely, you have to mod it out by K H. Okay. And now, so what is Lie G0? Well, so that must be an extension by this. So you just take 1h h and mod it out by one-dimensional space, 1 over h. Okay, so what I did for you is I constructed this diagram on the level of Lie algebras, and then you have to integrate. And here you use Lie theory. So you need to analyze the structure of G0, and G0 has symplectic group in it. It has some infinitesimal translations. And you can integrate those explicitly, and then it has a large unipotent part. But unipotent groups in characteristic 0 are the same as Lie algebra. So you don't. That's from this, it's not that difficult to construct the 0 tildes. That's the idea. All right. Are there any questions?
That's fun.
Sure. Yeah. Yeah.
Wonderful.
So this is the cross module that represents this two group, and here and this diagram represents a map from G0 to this cross module. So this is essentially Fedosov proof formulated in well, again, so he worked with smooth manifolds. Sometimes it's harder because you have to take care of conversions and things like this. But
can you explain a little bit more why this two group is represented by this simple cross module?
Oh, okay. So suppose you have any local ring A. Local ring. Local. My ring is local. Then, so what is a group of well, what is a group of well, first of all, any automorphism of A. So I claim that automorphisms or any local ring, automorphisms of modules over A is represented by this cross. So first of all, if I have an automorphism of A, then definitely so if phi is an element, then I can this gives me a map from modules of A to modules of A, right? So phi start maybe. Let's see. Okay. So now I have to explain that if my phi is add of some element A, then this gives me a map, an isomorphism between phi and identity. So and I guess so I need to, for every A modulo M, I have to construct for you an isomorphism between this A module and this A. And I think that this isomorphism is given either by multiplication by A or maybe A inverse. Figure out this. So that gives me a map, at least, from this cross module to this two group, right? And if you want to show that that's an isomorphism, even though strictly speaking, I don't need it for this argument, it's enough to construct a map from G0 to the subgroup. But if A is local, then well, you see any any autoequivalence of this category is given by a bimodule, which is projective as a left A module. But any projective module over a local ring is free. You can see that because it's an autoequivalence, it must be of rank 1. So it's given by, it comes from some automorphism of A. Okay? Very good. So that's the picture.
This will explain.
Well, there is a very small section in Bezrukavnikov Kaledin paper. They say that they learned this idea from Kansevich and Greenfield. And also it's implicit in paper by Delin on Fedosov quantization. And indeed, it's implicit there. I guess there is a paper by Van der Berg. It's called Global Quantization of Poisson Varieties. So it's very kind of detailed and very all proofs are there, but it's maybe 80 pages or more. And the main input is Kansevich formality, which I might state with the idea.
But he does it in general, Poisson.
Yes. But I mean, once, yeah. But the input is Kansevich formality. All right. So maybe I will just give you one kind of very basic, very important example of a canonical quantization. Well, in this case, it will be quantization of algebra. So suppose my X is a cotangent bundle Y. In this case, I have a symplectic form omega, which is D of the topological. And so how to construct quantization of this set? You can consider the algebra of differential operators on Y. So this is an algebra, and it has a filtration by the order. And you can apply the risk construction. So, well, what is this? This is a subalgebra of dy H generated by, well, of course, by H, or Y, and H times T. Well, I'm interested in the formal, so I have to complete it. So this is a quantization of this symplectic variety. It's not the canonical quantization, and even the category of modules over this is not the canonical quantization. But we can build from this the canonical. Now recall that for every line bundle, and a number, well, T, C, or in K, we can consider twisted differential operators. Line bundle L. So what is this? Well, I will give a kind of down-to-earth description of this algebra. Maybe if C is actually a number, an integer. Sorry, C is actually an integer. Then these are differential operators from, for example, C is 1, from A to itself. But the claim is that it makes sense for any C, for example, 1/2. So how you define this? So if you fix a trivialization of your line bundle, then this gives an isomorphism between let me right direction. Yeah. This gives me an isomorphism between du and du L. Of course, if the line bundle is trivial, then I do not do anything. And if I choose another trivialization, then so I have to explain for you what is the composition, and the composition is in this direction, alpha inverse pi prime. Suppose I have two trivializations, and I just need to explain for you the automorphic, construct for you an automorphism of this algebra. And this will be, formally, it will be, okay. So here is a formula. So f, so this is a map from du to itself, and it takes function f to itself, and a vector field theta to something else. Well, it's theta minus, well, c times, well, I take the Lie derivative. So what is f? So so phi prime composed inverse composed with phi, it's an automorphism of this guy, and this is f. That's an invertible function. If I have an invertible function and a number, I can construct an automorphism of the ring of differential. It's defined by this formula. It's sort of informally, it's conjugation by f to the power c. So having this, and well, you need to verify cocycle condition, you can glue this. So that's called the ring of twisted differential operators. It also has this filtration. And so canonical quantization. Canonical quantization. Maybe one remark is that which is we used in the proof that this is canonical quantization, is that so if you consider the opposite of it, well, if you consider the usual differential operators, even though the category of left modules is equivalent to the category of right modules, the algebras are different because the equivalence is provided by tensor product with the canonical. So here the formula is that this is isomorphic to d opposite dl minus c tensor with canonical. So in particular, d k y 1/2 opposite is equivalent to d k y 1.
But is it obvious that the canonical equilibrium doesn't satisfy this condition?
Yes, yes. No, you see,
I mean, this is going to be true for any S, right?
Of course, yeah, you just have to look at the construction of the action that I did. Right? Yes. Maybe I not go back to that, but yeah, that's obvious. So the claim that I wanted to make is that the canonical quantization of uh, the y is the category of modules over this. Well, first of all, you take twisted by one half of the canonical bundle, and then you consider this. So in particular, so there is a sheaf on X, which is a structure sheaf on Y. So it cannot be quite, it cannot be quantized, but if you have a square root of this, then it can be. Well, I said that there was a second statement in the theorem that I formulated about quantizations of Lagrangian subvarieties. So Y sitting inside X as a zero section is an example of Lagrangian. And the theorem says that if you have a square root of this, of the canonical square root of the canonical class of this Lagrangian, then you can quantize. You can quantize this structure sheaf. Well, you can quantize this as an object of quasi-coherent sheaves on X, right? This is well, if you have the square, and in fact, if this is actually a line bundle, then well, this D modules they act on this line bundle by definition. And this gives me points. All right, so that's this consistent. Right. So now
So could you say why, in view of what you just said, why is it that we have these two quantizations in this case? Why do we have the resalted as well as this correct answer?
We don't, because I have to choose it's no algebra. Because for this algebra, I will choose this square root of
yeah, but still you can consider the category of modules, D modules, usual D modules. You can consider modules over the Riesz algebra. So I'm not saying that there exists only one category of quantization, right? So definitely not. For example, yeah, I can twist. So a categorical quantization is a category together with an equivalence modulo H with the category of quasi-coherent sheaves. I can twist this equivalence by a line bundle. So there are many quantizations. I'm just saying that there exists one canonical that is given by the construction that I explained. So, and this is a theorem that you get precisely this. And I'm saying that the input in the proof of this theorem is any. But it's still non-trivial. I mean, it requires some work to prove that the answer is correct. That the canonical quantization that is given by that construction with Lie algebras, with formal geometries, indeed it's not, for example, it's not straightforward, but that's an input. All right. So now I want to explain the picture when characteristic of k is 0 is p. And I don't know actually what to do when p is 2. So I will assume that p is greater. So, well, in this case, well, so this has a this so I have x symplectic x omega. There is a new feature of this situation, namely OX has a large Poisson center. So namely, so what I mean by Poisson center, so we have the Poisson bracket, and this Lie algebra has a large center. Namely, p power of any function is in the Poisson center. That's Poisson. And well, if k is perfect, then that's everything. Otherwise, you have to tensor it with k. So that's So that means that, for instance, if I consider quantization of the algebra, then this commutator in quantized algebra, modulo h squared, it has large center. And you can ask whether you can quantize your symplectic variety in such a way that the center is preserved. So fact. So if x is spec a 0, and you have quantization ah, so it maps to a 0, and if any central Poisson central lifts through a central element here, then omega must be exact. So, well, there could be quantizations, of course, that do not satisfy this property, but they're not kind of central. So that's one remark. Another remark is that, in fact, well, I don't know what to do with for general symplectic varieties, because the first kind of input in the proof in the construction of quantization was Darboux. So second remark is that Darboux fails. Well, that's because you have exact because if you say over formal disk, you consider something like 1 plus x to the p minus 1 dx, which 1 plus minus 1 dy. So this form is not that's form over, I consider it over formal disk, but it's not exact. So they definitely cannot bring it to the form dx slash dy, right? So even locally, like structure of symplectic varieties is complicated. Yes.
They don't have the sexual local model, but you associate of the way characters, touches, and the energy culture, correct?
It would be very nice, but I don't know. I mean, it seems that yeah, you can consider, for example, symplectic forms with the property that its Corti operator is equal to itself. Saying that it's exact means that its Corti operator is 0. You can impose some other condition, but it's not clear to me that you have Dervula. So I will consider myself, restrict myself to very special symplectic varieties. So a restricted structure on X omega is a class eta in H0 of X with coefficients in omega 1 modulo D such that D of eta is equal to. So so a restricted structure is kind of it's a primitive of omega, but which is not kind of globally defined, right? It's so this is a very restrictive condition in characteristic. The existence of this structure is very restrictive in characteristic 0. In characteristic P, it's less restrictive. Well, in characteristic 0, for instance, if X is smooth projective, then by Hodge theory, you can't have symplectic forms or even global 2 forms that are locally, Zariski locally exact. That's not possible. But in characteristic P, it is possible. Or maybe another example, there is a moduli space of the RAM local systems on a curve. It is known that it has a symplectic structure. And the miracle of characteristic P is that this symplectic structure is always all P. But it's not exact over Rations.
The RAM.
The RAM, right. If you consider beta, then it's not. So what I'm going to do is I will consider only restricted symplectic varieties, and the theorem is that they admit canonical categorical quantization, but kind of a new phenomena here is that this quantization is the kind of in characteristic 0 we consider it formal quantization. So H was a formal parameter. And there were many reasons for this. Well, one reason is that even like for the cotangent bundle, you can consider differential operators, Riesz algebra, differential operators with parameter H, but you cannot localize this algebra over the cotangent bundle. Like in the localization of non-commutative algebras, it's complicated thing. So it's not a sheaf over nature. It's not a sheaf over the cotangent bundle. But in characteristic P, because the algebra of differential operators has large center, you can do this. You can localize. So the new kind of okay. So suppose I have any x eta has canonical categorical quantization. Quantization over, so Kukoc still H, but this is a category that leaves over P1 times, well, the Frobenius twist, right? So X prime is this X spec A over Frobenius. So with the following, so the coordinate on P1 is what I previously called H, and my quantization was defined only in the formal completion of P1 at the origin. So there is a new, the second factor, X prime. So there is a notion of a abelian category over a scheme, even over a stack, but over a scheme. So this is an abelian category over this scheme. It means that well, what is it? It's for well, how you define the notion of a quasi-coherent sheaf on a scheme. That's assignment for every affine scheme mapping to your scheme. You have for any spec R mapping to this guy, you have a R module satisfying various properties, various structure. And here, definition, there is a notion of abelian category over any scheme, which is, I think, due to maybe Jacob-Uri or Dennis Gates-Gorey. So that's basically the same thing. So for every affine scheme mapping here, you have a category over R. So that's kind of the expresses the idea that this category has a value-large functions on X prime. So if X prime is affine, then that just means that it's a single category over the coordinate ring, such that it's an abelian category, right? Such that if you take Kukoc H restricted to 0 times X prime, you get Kukoc X. If you take this and restrict it to infinity times X prime, what do you get? So I thought this will be Kukoc of X prime. And in fact, I can even tell you what this category is over P1 minus 0 times X prime. All right, so that's the following. That's the category of modules over some algebra. So you can consider the algebra of differential operators on X and then I will have agents. And what you can do with this algebra, I can look at its central reduction. So I'll explain what it means here, what I mean here. So the algebra of differential operators is has a large center, and there's functions on the cotangent bundle. This is O of t x prime. So if you have any subscheme here, you can just restrict you think of dx as an algebra, quasi-coherent sheaf of algebras over this space. And if you have any closed subscheme, you can restrict your algebra to this subscheme, right? So for example, you can consider if eta is actually represented, well, this class is represented by one form, global one form, you can consider its graph. And this sits here. And what I mean by this is this restriction of my algebra to this graph. And in fact, if I modify eta by an exact form, then even as an algebra, the result does not change. So the two restrictions are the same. So dx eta is canonically isomorphic to dx eta plus dA. And therefore, you can define this algebra for any restricted structure. So that's looks. I think I need to. Well, have 4 minutes. So right. I think I maybe just to finish the formally the statement of the theorem. Let me. Okay. Right. So maybe that's another part. So for any Lagrangian, well, sitting inside X, such that eta restricted to a is 0. Well, where this formula comes. So, and this formula comes from an observation, a very important observation due to Sasha and Froman, that the following. So, suppose I have any y, and I can consider the cotangent bundle the y. Sorry, that's cotangent bundle. And this has a tautological form, eta, omega 1 of x. Then you can do two things. You can consider the algebra of differential operators on y. On the other hand, you can consider the algebra of differential operators on n, and you can take this central reduction that I explained. Even though these algebras are not isomorphic, the category of modules are canonical equivalent. So why is it so good? Well, you see, so in the model example of the cotangent bundle, our quantization is supposed to be this, maybe up to twist with twisted by some. Well, the category of modules does not change if you twist by an integer power of a lambda. So it's just supposed to be this. And this isomorphism, this equivalence, says that you can actually express this category of D modules in terms of something that uses only the cotangent bundle, the symplectic variety itself, together with a restricted structure. So this depends only on the restricted structure. So at least this is kind of the motivation. This explains why you can expect something like this. All right, I think I have to stop here.